All right, thank you. Yeah, so my name's Connor. I work at PI right now. Nominally, I'm there to study quantum field theory. And when it comes to quantum field theory, there's a lot that we only know how to do in 2 dimensions so far. And that's because in 2 dimensions, it's possible to have a lot more space-time symmetry than you can have in general. So there's a result by Coleman and Mandula from the 60s, I believe, showing that space-time symmetry beyond Poincaré will force the initial momenta in 2 to 2 scattering to be equal to the set of final momenta. And if you want to have analyticity in the scattering angle, then this implies that, well, yeah, it implies that P1 and P prime 1 are equal, same with P2 and P prime 2. But in 1 plus 1 dimensions, there is no scattering angle, so this consideration goes out the window. And it's possible to have higher space-time symmetry. And in fact, in many models called integrable quantum field theories, you do have higher space-time symmetry. So there's a version of this that applies in the world of conformal field theories, which lie outside the assumptions that Coleman and Mandula made. And I'll talk about what those are. And in particular, you have something called the Virasoro algebra in 2-dimensional conformal field theory. So I like 2-dimensional CFT because it is a language for describing critical phenomena and also string theory. But I'm not going to touch on those subjects. I'm going to talk about a particular mathematical structure, which was first noticed in this context. Samuel-Lodgkov called it the W-algebra in 1985. So that's one paper you can look up. A lot of this talk is based on a 1992 review, and another large portion is based on a set of lectures that Chris Beam gave in the 2021 Bootstrap School, which was fully online. So the lectures were recorded, and you should be able to find them. So a conformal transformation is a map from some coordinates which preserves angle. And what that means is that the line element is preserved up to some function of the coordinates. And in everything I discussed, the line element is going to be the Euclidean metric on flat space. Which becomes very nice if you use complex coordinates. So if z and z bar are x plus or minus x1 plus or minus I x2. So in that case, it's very clear which transformations will leave ds squared invariant up to some overall function. These are going to be the ones where z goes to some function that only depends on z. Z bar goes to some function that only depends on z bar. So there's some holomorphic reparametrization freedom. Now these holomorphic transformations are generated by vector fields. And the basis for them is given by simple powers like this. And these satisfy an algebra. So you can see what the commutation relations are between the L's and the L bars. And you end up with this. And similarly for the L bars. So there's one more term which we need to add, which you cannot get by looking at the vector fields, but it turns out to be very important. So it's parameterized by this number, which is called the central charge. And it's a term that you can sometimes use to deform a Lie algebra using a new generator that commutes with all of the other generators. So the Virasoro algebra admits a central extension. And one way of thinking about why you would want to consider central extensions is to think about the fact that states in quantum mechanics are ambiguous up to a phase. So observables come from inner products, come from the norms of states, the norm squared. So that means that if you have a symmetry group which acts on states, the representation with which it acts on the states only needs to be projective. So given a symmetry group, Wigner tells us that the state picks up U of G, where U is either a unitary or anti-unitary transformation. But for elements continuously connected to the identity, it has to be a unitary transformation. And then because of this phase freedom, the group law is allowed to look like this. So a phase that you add to a Lie group becomes a constant that you add to the infinitesimal Lie algebra. But we can say more. So the condition for associativity has to look the exact same. That imposes a condition on alpha. And we can phrase that condition nicely if we define a map between n variable functions and n+1 variable functions on the group. And what this map will do is give you a term where you drop G1 where you drop Gn+1, and then a sum of terms where you drop something in the middle and multiply. So I have gk times gk+1. Gk+2 up to Gn+1. So now we can phrase associativity as the idea that, well, okay, first of all, this is a differential. You can check that this corresponds to 0. We can rephrase associativity as the condition that D annihilates alpha, so alpha is closed. And finally, what happens if alpha is exact? What happens if it's equal to D, D of some beta, which depends on one element? Well, in that case, it turns out that this phase is actually fake. We can remove it by just redefining these unitary transformations with that other phase. So central extensions of a Lie algebra signal projective representations of a Lie group. And because of this, projective representations are classified by the second group cohomology. So that's just an aside that I thought this audience might like. It's very academic when talking about the Virasoro algebra because we're not going to use any global form of the Virasoro algebra. There is a Lie group over the reals having Virasoro as its Lie algebra. It's called the bot Virasoro group. But there's no complexification of it. And complex analysis is very important in conformal field theory. So I'm just going to talk about essential extension as a Lie algebra thing. So it's important to discuss the states of any quantum mechanical system, in particular, two-dimensional conformal field theory. And if we find some way of specifying the states, that gives us the structure of a vector space. But that's not enough. We also need to equip that vector space with an inner product. And there's not a unique way to do that, but there's a very convenient way called radial quantization. So what is that? Well, it's based on letting your Hamiltonian be the generator of translations in the radial direction, so scale transformations. And that means states are going to live at some fixed radius. And you shouldn't take this too literally, but it goes along with the idea that you can define a time to be the log of the radius, in which case this complex Z plane is mapped to a cylinder with time running vertically. And we know that if we use a Hamiltonian to evolve a state from 0 to finite time, then Hermitian conjugation of this is going to take time to minus itself. So we can think of there being some in state at time t and some out state at time minus t. And what that maps to on the plane is going to be an in state at radius r and an out state at radius 1 over r. And all this is to say that if you quantize the theory in this way, then we can figure out what the Hermitian conjugate of a generator Ln has to be. It has to be Ln conjugated by 2 inversions. And from the explicit vector fields, you can show that this just means you flip n to be minus n. So now that we have a notion of conjugation, we can see whether the inner product it defines is positive, definite, or not. That is not automatic. It introduces constraints. So because we're using a Hamiltonian based on L0 and L0 bar, what we should do is work with a set of states that diagonalizes the action of L0. So we'll just label them in this way. And our states should fall into a representation of the Virasoro algebra. And highest weight representations are annihilated by all of the positive integer n's. this defines the structure of a Verma module, and I'll justify why we use this structure a bit more in a second. But a Verma module starts with the highest weight at level 0. Then it has this descendant, which comes from acting with L-1 at level 1. And then it has 2 descendants at level 2. Three at level 3. And so on. And I want to stress that we only need L-1, L-2, or L-2, L-1. We don't need both of them. This is a linearly independent set because if we had the other order, we could just use the commutational relations to get some expression in terms of these. So at every level, the dimension of this module is P of the level, where P is the number theoretic partition function. How many ways can you write L as a sum of integers? So what we want to do for every Verma module individually, which could appear in a theory that we try to build, we want to make sure that the Gram matrix has all positive eigenvalues. And the Gram matrix is a matrix of all the possible inner products of these states. So states at one level are orthogonal to the states at another level. So the matrix is block diagonal. It's going to be M0, M1, M2, and so on. And we can use this conjugation rule to start figuring out what these are. So M0, what is that? It's the inner product of H with itself. We take it to be normalized. So that's just the matrix, the 1-by-1 matrix whose entry is 1. That is pretty simple. M1 is also going to be 1-by-1. And using the commutation relation and the fact that L0 acts diagonally, the entry of this matrix is going to be 2H. And that gives us more information on why we should work with Verma modules. So if there was a state that did not fit into a Verma module, and the actions of positive L's kept giving something non-zero, you would be able to lower the L0 eigenvalue indefinitely. And if you can make this arbitrarily negative, then you know you're living in a theory which is not unitary. It doesn't have a Hilbert space structure. So it must be possible to take states not annihilated by Ln, by positive Ln, and fit them into representations whose highest weight is annihilated by Ln. So as long as you can do that, we still have a simple condition for getting unitarity. Just make sure these weights are positive. And then at level 2, we start to see something more interesting because the matrix involves the central charge. So you can keep going, you can compute M3 and M4, the matrices get bigger and bigger. And I'm not sure how hard this is in practice, but there's a pattern that will take over. At least if you compute the determinant, you'll see that the determinant always factors completely over the reals and has a lot of degenerate roots. And in fact, there's an explicit formula for the determinant due to cuts. So there's some constant which is known. And then I'll write it this way. The product over non-negative integers lambda and lambda prime such that this product is less than or equal to the level and then you have h minus a root, which is some function of the central charge, to some power, which is a partition function not of L, but of L minus this product. So before I even write down the formula for this root, this structure tells us a little bit about the representation theory of the Virasoro algebra already. Because we know that the dimension of the level L subspace in a Verma module is P of L. But if the number of vanishing eigenvalues of the determinant is P of L minus something, then what that suggests is that eventually in this tree that's getting bigger and bigger, we find a state that has zero norm. And as soon as there's one state that has zero norm, anything built on that state by acting with further copies of L is going to continue to have zero norm. So the level minus, the initial level minus the one where that first appears is the head start that this vanishing tree gets on the whole tree. So that's why you have partition function of this difference. And this tells us that the specific values of the L0 eigenvalue, the specific values of H, which allow you to have these trees of states that have zero norm. These are labeled by two non-negative integers, and the level where that state of zero norm first appears is given by this product. So there's a lot you can glean by staring at this for a while. But I want to write down a formula for this root. So first of all, it's convenient to write it in this parametrization. Maybe 12, yeah. We write the central charge in this way. And then these special weights, which give rise to states at some level of zero norm. They have this parametrization, and I need to tell you what beta is. So lambda alpha plus lambda prime alpha minus 1 over root 2. Now I need to tell you what alpha plus and alpha minus are. They are solutions to this quadratic equation. So the only proof I know of this formula is very physicsy, so I won't cover it in detail, but it involves capturing this central charge using some auxiliary theory of charged free bosons. And when the charges can be expressed in this way for integer lambda and lambda prime, that allows the correlation functions of them to be made neutral when you insert operators with alpha plus and alpha minus charges an integer number of times. And alpha plus and alpha minus are special because when they solve this equation, that means they can be inserted for free without spoiling conformal invariance. So that's a whole thing called the Coulomb gas formalism. I don't want to get into that. But what I want to say is that you can plot these roots in the CH plane. And what you'll quickly find is that they all lie on the left side of this line, which says c equals 1. So you have a bunch of curves where the determinant vanishes and therefore some eigenvalue vanishes. And over here, everything's guaranteed to be positive definite. So if you wanted to pick a line, if you wanted to pick a point on the left side of this line, let's say this one. Oh look, I've plotted the first couple of curves. As long as I stay to the right of them, then there's no negative eigenvalue I've detected yet. But for almost every point in this half space, you'll be able to keep going and plot more curves such that you eventually do encircle this point. So there's some kind of density going on. And it turns out that if you want the central charge to be less than 1, the only way to get the only way to avoid negative norms is to have a point that lies exactly on one of these vanishing curves. And in fact, it has to lie exactly on a point where two of them intersect. So then all of your eigenvalues are either positive or 0. And you get to construct smaller representations by modding out the ones that give you an eigenvalue of 0. So if the central charge is less than 1, this is the only way to have a healthy quantum mechanical theory. And it automatically gives you very nice information about the theory. It tells you what all of the energies in it are, all of the eigenvalues of this Hamiltonian. You know right away just from the fact that it's a healthy theory and the central charge is less than 1. And there's also a way to work out the correlation functions of those theories. So morally, what you would do is take the correlation function you're looking at and use this completeness property to insert a complete set of states anywhere you want. So you can pick any, so you can put some operators on the left of this thing and some operators on the right of this thing, and you have to get the same answer no matter where you put it. And that gives a set of constraints called the bootstrap constraints. And there's a series of papers. Ever since this determinant formula was found, a series of papers worked this out and solved all of the two-dimensional conformal field theories with unitarity and central charge less than 1. So this construction is called the solution of the minimal models. So that story could be a talk by itself. But what I want to mention is that it applies to the Virasoro algebra. And the Virasoro algebra, it can be seen as a trivial example of a W-algebra. To get non-trivial examples, you have to consider its universal enveloping algebra. And one reason for why you might do that is that these considerations here allowed you to find some exactly solvable models, which are very rare in quantum field theory. And maybe if we go beyond the Virasoro algebra and consider extensions of it, we'll be able to find a set of exactly solvable models yet again and just keep growing the set of models where we can do exact calculations. So that turns out to be the case. If you keep going with the derivation of this determinant formula, you can think about what happens when you have many families of, you can make a multi-component generalization. So instead of just two types of charges that you insert, alpha plus and alpha minus, you could have 2R, where R is some rank. And then you get a generalization of this formula. So instead of lambda and lambda prime being non-negative integers, i.e. dominant weights for SL2, you could have lambda and lambda prime be dominant weights of some Lie algebra. Let's say a simply laced Lie algebra. I think there are subtleties otherwise. And then the generalization of this will be essential charge being less than rank G. Okay, now it's 24. Because we have file vector squared. And then this special weight, which is the root of the determinant, that'll be some inner product with the killing form. And then the analog of this formula here will be a sum using components of these weight vectors contracted with the fundamental. So we have this determinant, which is a structural property that's important for making sure you know how to build healthy theories respecting the Virasoro algebra. And it, as a side effect, it also gives you a lot of information that you can use to solve some of those theories. And if you just take the proof of this formula and apply some natural generalization, you end up with something that probably doesn't have to do with the Virasoro algebra anymore. It probably has to do with some other algebra, even though I haven't told you what it is. And it turns out to be a non-trivial W-algebra. So yeah, I think we're about halfway through the talk. And for the rest of the talk, I want to try to put on my mathematician hat and tell you about some formal considerations for how you should think about this extension of the Virasoro algebra. Yeah. So it's the number of simple roots that the Lie algebra has. The number of nodes in the Dinkin diagram. I don't know how much. So let's be formal and write a definition. Field on a vector space V is an element of linear maps from V to itself. It is a series in Z and Z inverse such that every coefficient is a linear map from V to itself. With an additional property that even though you can have as many negative powers as you want in the whole thing, for every fixed state that you act on, you only have finitely many negative powers. So, such that for all vectors V, A of Z acting on V is now a finite Laurent polynomial. So it's in this space. So two brackets here will mean that I'm not talking about polynomials. I'm not talking about finitely many powers of Z and Z inverse. I'm talking about potentially infinitely many powers. Two round brackets here will mean that the infinite powers go one way but not the other. You can go as positive as you want, but you can't go as negative as you want. So the next thing I want to talk about is a product of two fields, A of Z, B of W. In conformal field theory, we would call this the OPE, the operator product expansion. But at this abstract level where like a minimum amount of information has been defined, it's so far just a multiplication of formal power series. So we know how to compute that, but it's not guaranteed that it satisfies all the properties we would expect if we're used to conformal field theory as it appears in physics. So there's another definition. These fields are mutually local. If we take U and V in the vector space and its dual, and get these pairings to be compatible. So what does compatibility mean here? Well, these formally live in different spaces. So here there's a global bound on the negative powers you can have with respect to W. And then for each power of W, there are only finitely many negative powers of Z that you can have. But in this whole expression, you might have arbitrarily negative powers of Z. And for this pairing, it's the other way around. And compatibility means that there's a function which is not too singular, such that both of these are expansions of it. So expansions of the same function in this space. So you can have plenty of positive powers of Z and W, and only finitely many for Z inverse, W inverse, and Z minus W inverse. So the typical example here would just be the function 1 over Z minus W. So that's a function in this space. And there are two Taylor series for it that you can write. If Z is greater than W, you get one. If Z is less than W, you get the other. So that controls whether you get this type of expansion or that type of expansion. So the expansions you get from that procedure will be compatible by construction because you got them from a single function in this space in the first place. So now there's another definition. Z created vertex algebra is a quadruple. It's going to be a vector space, which we can write as an infinite direct sum of finite dimensional spaces. This is the Z-graded part. It's going to be a distinguished state in V0, which we can think of as the vacuum. It'll be an operator called the translation operator, which maps Vk to Vk plus 1. And it's going to be something called the state operator map. Which satisfies a few properties. So okay, maybe I'll write it this way. So what Y is going to do is it's going to take V to a field on V, one of these. So if a vector has grading H, which you should think of as an L0 eigenvalue, then Y of that vector and Z is going to look like this. Okay, let's say this is A. Yes, that's just a convention. When y accepts the vacuum, it's going to give you just the identity map on V. Yeah, y of some state acting on the vacuum is going to be free of singularities, so it's not going to have any negative powers inside it. And y of the state at 0 acting on the vacuum is just going to be the original state itself. Oh yes, and then the properties of the translation operator. So the vacuum has to be translation invariant. And finally, y acting on a state which is itself acted upon by the translation operator is going to be the operator you get with just the state acted on by the formal derivative. So that's what we would hope to be satisfied if we're going to use the derivative notation for this, vacuum notation for that, and so on. These are operators. These are endomorphisms of V. Oh, you're right. Okay, there's one more axiom. I keep thinking I'm done, and I'm never done. So this one. Yeah. So yeah. So yeah. AM is a map from the vector space to itself, but considering this grading, whenever it acts on yeah, VK, it goes to VK minus M. Yeah, so does that answer your question? So that's a Z-graded vertex algebra. And now getting close to what we want, a vertex operator algebra. It's a special Z-graded vertex algebra. With some field having weight 2. L naught is the grading, and L minus 1 is the translation operator, and these linear maps acting on weight spaces have the Virasoro commutation relations, which are still on the board, so I don't want to read them again. So it's a vertex operator having, which is at least as big as Virasoro, essentially. But it can be bigger, and we want to consider ways of making it bigger. So if somebody were to just hand you a vector space and asked you to, I still have not listed all the axioms. Yeah. Yeah. So here, I guess. Yeah. I guess I'll just specify that it's part of vertex algebra already. You don't need to be in a vertex operator algebra to have this one. All of these fields that you can get by taking some state and acting with y are mutually local. That's why it was a big deal to define that initially. Great, so if you just had a vector space and you wanted to make, and you wanted to make a vertex operator algebra out of it, this would be the hard part. Naively, you would expect that it would take an infinite amount of work to just keep plugging in different states from that vector space into y and keep checking that you get mutual locality for all the possible results. But there's a theorem that helps us. So if you have mutual locality for two fields, this normal ordered product preserves mutual locality. So the definition of that is going to be here, it's going to be a little non-trivial. So it's the way of combining the A coefficients and the B coefficients such that this axiom is satisfied. So if these A's and B's were just numbers, if they were not linear maps from a vector space to itself, then they would commute product as the actual product of the formal series expansions. But these are operators because this is meant to be applied to quantum mechanics. And they're operators for every mode of a field. So this is meant to be applied to quantum field theory. And in particular, this definition is nice enough that we can set W and Z to be the same number to give us just a single field at a single coordinate, and we would be able to satisfy this axiom. So normally in quantum field theory, we have to be very worried when we multiply two fields, two operator value distributions at the same point. This is singular, it needs to be renormalized. And here, there's an implicit normalization scheme that's been used, this ability to say that in this normal ordered product, we talk about A times B when it's convenient, and we talk about B times A when it's convenient, in order to renormalize it and remove these singularities. So that's like a physical motivation for this definition of normal ordering. And normal ordering is very nice because if A and B are mutually local, then AB will be mutually local with them as well. And moreover, mutual locality is equivalent to the Jacobi identity for all of these AMs and BNs. So we're getting close to the goal now. There's a way that we can avoid having to do an infinite amount of work for an arbitrary vector space. We can try to define things such that all the work is done for a finite number of fields, and then all of the other fields we might expect to consider are just normal ordered products of them. So that motivates us to consider strong generators. That is the fields that you can use to build any other field if you successively take normal ordered products and derivatives. So you can try to construct specific examples of vertex operator algebras that obey these properties by saying how many strong generators you want to have for each conformal weight, like each value of h. And then the vector space is just going to be the minimal one that you can build by taking all of these strong generators and their derivatives and products and acting on the vacuum. So this sort of constructive approach I was talking about before, where I wrote some highest weight state and then said, okay, the rest of the module is just going to come from the action of these Virasoro modes. So we have to specify some strong generators and then check the locality conditions by checking some Jacobi identities, and that can be put into a computer. Yeah, I think I'm going to erase this. Okay, yeah. So first, I guess there's one other very simple statement to write. It's just how do we invert this? Well, convert this with a contour integral. 0. Whatever the power is. And that means we know how to compute commutators. So if we if we have a commutator of 2 modes, that'll be 2 contour integrals. You'll have something like z being outside W minus z being inside W, where they're both around 0. That will convert to z around 0 and W around z. You can work this out. And then what you'll see is that the singular behavior as z goes to W, so these finitely many singular powers are going to be the ones that control what the commutators are, because you could evaluate contour integrals with the residue here. So we've seen the Virasoro algebra already. Let's just belabor that point so you'll believe me a little bit more that this works. So T of Z and T of W are, of course, mutually local. They're the same operator. So what we're going to have is just, okay, so yeah, so they have this weight of 2. In fact, okay, let me be consistent and write them as L. This is the stress tensor. I usually write T, but here it's better to write L. So they have a weight of 2. So the maximum singularity here can be Z minus W to the 4th. Then there'll be some other coefficient with L having weight 2. And that means you can have Z minus W squared. And then some other coefficient with the derivative of L at W. And this is singular, and then nothing else is singular. So knowing this, you can say, what is the commutator of Lm with Ln? Well, it's going to be these 2 contour integrals minus those 2 contour integrals. Rearrange the contour integrals and plug in this expansion, and you'll get some ansatz which looks like this, except it'll have x, x prime, and x double prime. And then you'll say, how do I make sure the Jacobi identity is satisfied? And you'll get solutions for x, x prime, and x double prime. And what you'll see is that x had to be c over 2, x prime had to be 2, and x double prime had to be 1. So that's the algebraic algorithm. So now we want to take the next step, and we want to say, okay, this strong generator had a weight of 2. Let's add some W of Z with the weight of 3. So the algebra we end up with will still have this for the 2 L's, because it'll be a vertex operator algebra. We want it to still have Virasoro always. But we'll need to consider L of Z times W of W. So what's a good ansatz for that? Well, weight 2 plus weight 3 will give us some Z minus W to the 5. But it's pretty easy to see that you can work out pretty quickly that the coefficient of this has to be 0. Can you have something like this, for example? Z minus W cubed. Well, initially you might expect to have this, but then associativity would quickly kill it, because if L with W could produce L, then by Jacobi it looks a lot like L with L could produce W, and we already know that that's not the case. So without doing a huge amount of work, we can see that this term is absent. The terms where we cannot see that so quickly are going to be y times W and y prime times the derivative of W. So these need to be solved. And the hardest one happens when you have two W's. Yeah, so just write everything that could possibly show up. Please stop me if I write anything suspicious. Keep writing T instead of L. This habit is dying hard. Stress test result. Stress test result. And finally, this. Right. So when we go to commutators using the contour integrals, so we'll get Virasoro, of course. We'll get Ln with Wm is some function of Wm plus n. And then this big one. So you'll have these functions of m and n to play with as you try to make sure the Jacobi identity is satisfied. And I want to write them down just so you can see what they look like. Yeah. Okay, F is very simple. G should be very simple. Yeah. H1 is the most complicated. And fun H2. So there's a unique solution, and it's called the W3 algebra. And that is what realizes this prescription where lambda and lambda prime are no longer weights of SL2, they're weights of SL3. So you can keep going. You can add a generator, a strong generator of conformal weight 4. By the way, I think weak generator would be, yeah, so L and W are strong generators of this W3 algebra. I think you could say that W alone is a weak generator because 2 W's produces an L, but it's more useful to consider strong generators. So you could consider a case next where you have conformal weight 4 as well, so 2, 3, and 4. That would give you the W4 algebra. And it would quickly become very difficult to show that there's a unique solution and write down stuff like this. But there are some theorems which I wouldn't have time to cover, and I haven't learned them properly anyway about like showing existence results for these W-algebras, even if you don't know how to write them down so explicitly. So there's something called Dirichlet-Sokolov reduction, which is like a BRST quotient procedure on some much simpler algebra that allows you to generate W-algebras. So these sort of exemplify what physicists like to do, which is find a way out of no-go theorems. If you're in two-dimensional CFT, then restrictions on higher spin space-time symmetry sort of go out the window, and you can find a whole zoo of W-algebras. I've tried to briefly sketch how you might construct Wn algebras, but there are even more exotic W-algebras where sometimes you can't get them to exist for arbitrary central charge. Sometimes they fix the central charge to a unique value as well. So it's either like a very good thing or a very bad thing, because you might have hoped that you could classify, you could get close to a classification of conformal field theories in the early days. And this is telling you that the classification, if you can find one, is probably going to be very complicated. But yeah, thanks for your time. Which Z? Yeah, so A of Z is the field on the vector space. Yeah, so the way it goes is you say how many fields are going to be strong generators. So here we made the choice that it's going to be one field of spin of conformal weight 2, which we know everything about, and then another field of conformal weight 3, whose properties we're trying to solve for. And then everything, yeah, so these have expansions in terms of like L, M, and W, M. Yeah. Everything in the vertex operator algebra, every state there, by assumption, is going to be just um, these modes acting on the vacuum. So we've limited the vector space that way. So yeah, and I was checking the Jacobi identity for the L's and the W's. On the right-hand side of this relation, the modes of the product of two L's, this normal ordered product, that showed up. But this theorem about locality lifting to the products, that's what prevents us from having to check like double LM, double LN, which is going to be some mess, and then keep continuing on forever. So yeah, we don't need to do that. Yeah, so yeah, you were asking about the contour integral. This is how we go from, yeah, like this mutual locality can be phrased purely in terms of these Laurent expansions as well. It's just that we might be more used to checking it for commutators like this. There's just a one-to-one correspondence between these expansions, but yeah, between the singular expansions and the commutators. So this contour integral is how we go from one to the other. Yeah, does that answer your question? So specified in this kind of a way? Okay, yeah. Yes. Yeah. So I hope it's not disappointing to tell you that it's it's just going to be um, yeah. So y of L minus 2 on the vacuum at Z is going to be L of Z. And same with W minus 3. So it's always the negative mode that corresponds to the conformal dimension. And then I guess for normal ordered products, it would be, you would have both of these acting on the vacuum. And then, yeah, and normal ordered products are not commutatives. It's expected that you would get different ones, L minus 2, W minus 3, or W minus 3, L minus 2. Yeah. Yeah, if you have, okay, so lifting the action of y to modules of the vertex algebra is an interesting question. Um, I, there might be some some extra ingredients there. But if you're just acting on the vacuum, and you act on it with a bunch of L's, a bunch of W's, like all the modes that this specification of the vertex algebra would give you, then there might be some calculation to do, but I think you do always know what Y gives you. It's always going to give you some, like maybe not L itself or W itself, but some normal ordered product with derivatives and like a linear combination. Like, yeah, I think going through this will always get you what that is. Yeah. Yeah, like cyclic arrangement, sum of 3 is 0. Absolutely. If you change these coefficients even a little bit, it all goes to hell. Oh, I think it's not going to be 0. You can have states that have a vanishing second derivative, I guess, but normally you would need to keep second derivatives. You would probably like the literature on BRST quotients of vertex algebras, or like the supersymmetric generalization of vertex algebras. Yeah, there's definitely interesting stuff I've seen along those lines, but I haven't seen it show up for this translation operator that